Welcome to Compass, which is organized carefully by Ronald, and then Igor's presentation about Mesoscale eddies beyond diffusion. I heard about his last name way before I met him, because his father is a very famous physical oceanographer in Russia. And then Igor, I think, came in the early 90s after Cold War ended, and then to MIT to work with Joe Pedlowski. He's also super famous. He's the author of the first, I think, physical oceanography book. I met him, of course, several times. Very kind guy. And after graduating from there, he went to University of Washington. But then we were able to successfully bring him here. What was it, 20 years ago, 20 some years ago, right? 18 years ago, and he has been great for our department. He's a very kind guy, working mostly on theoretical and numerical modeling of geophysical turbulence. He was teaching GFD2 for a long time, and I inherited a climate course from him, which was originally, I think, designed by Amy and somebody else. I enjoy teaching it every semester. And then Igor has been our chair for about 2 years now. He's doing a great job. And I look to his, I served in many of his student committees, great committees, and I look forward to his talk.
Okay, thank you, Taman. Thank you. Thank you very much for your introduction and kind words. Appreciate it. Okay, so here's the title of my presentation. I also list collaborators on this particular study that I will talk about. My former PhD student, Yuyan Blue, whom I was referring to, who is now at Florida State, my old friend and colleague. I was 17 when I first met him. Pavel Perlov, who is at Imperial College, and he was heavily involved in the project I will talk about today. And his postdoc, Michael Haik, his former student, Lorin's son, Irina Rybina from Moscow Oceanographic Institution. And so that's a group of people that I need to thank today for their collaboration on this study. I was asked to talk a little bit about my career, how I ended up here in this room. So I promise to be brief. I guess it all started for me from entering the MIT Woods Hole joint program in physical oceanography. At that point, I was 22, 23, something like that. And I came to this country from Russia. Actually, it was Soviet Union at that time. So I had a lot to learn. And I was extremely privileged to have a wonderful Joe Pedlowski as my advisor, as my mentor. Joe is a brilliant scientist, a fantastic mentor, and just a wonderful human being, a wonderful man. He taught me a lot, giving me a great example of brilliance, kindness, and integrity. A rare combination. And I learned a lot from him, and for those of you who do not know Joe personally, you're probably aware of his book. You should be aware of his book, at least, right? Geophysical fluid dynamics. And my study was on radiating instability of non-zonal ocean currents. Sounds really scary, especially radiating part. And it was a lot of theory, equations, simple models. This is actually a page from my first paper, or second paper with Joe. And I was really proud of the amount of math. I thought the more equations, the better. You look smarter. Actually, you don't. Anyway, so that study was highly idealized, a lot of analytical work, equations, assumptions, and a lot of guidance and patience from Joe. I am really grateful to this man. Right, and at some point you're done with your PhD studies and you need to move on, and they usually tell you to move to a new place, to broaden the group of people you know, to broaden your horizons. I decided not to leave Boston, but to change the topic of my study completely. So I entered the group, another joint program, very different, MIT joint program on science and policy of global change. And started working with this two wonderful scientists, Peter Stone and Joachim Marotsky. Peter's retired and Joachim is at Max Planck Institute at this point. Right, and that was a big change for me. It was like entering completely different world. Instead of looking at mesoscale eddies, instability, and writing equations, I found myself running models, ocean models, coupled atmosphere ocean models, talking about climate change and variations in large-scale ocean circulation on a scale of tens and hundreds and thousands of years. So this we actually designed a coupled atmosphere ocean model of intermediate complexity, which is this kind of models that we knew at that time. They are simple enough to understand and interpret, but at the same time they're sophisticated enough to include important effects of that important processes that play a role in climate change. So that, yeah, this picture is from that study. It's meridional overturning circulation, the stream function for meridional overturning circulation in the Atlantic Ocean, and I ended up making a lot of plots like this because I spent significant amount of time studying this large-scale phenomena, the AMOC, the overturning circulation in the Atlantic and the rest of the ocean. And again, I'm extremely grateful to the guidance of this tool. Okay, so well, at some point I had to leave Boston. So my next move was to University of Washington, where I became research faculty at the Department of Atmospheric Science, doing oceanography at that department. A little awkward, right? I collaborated a lot with Edward Sarachek, who became my close colleague and friend, and we did several studies again on large-scale circulation, meridional overturning circulation, trying to understand mechanisms that explain variations in this large-scale current. Again, looking at the processes on a scale of hundreds and thousands of kilometers and the time scales of hundreds and thousands of years. Very slow, large-scale events that are important in climate and ocean dynamics. And then later, and I stayed at the University of Washington until 2007, and as I learned more and more about ocean dynamics and ocean circulation and its importance of climate, and as I was able to run numerical simulations at higher and higher spatial resolution, I became aware, I mean, people knew it before, but I became aware of the importance of the connection between the mesoscale world and the large-scale world. In the beginning, I felt that like there is a big gap between the studies of mesoscale eddies, barochenic instability, and large-scale ocean circulation that is important in climate. Actually, that gap narrowed for me personally over years, and I realized that the small-scale processes, the mesoscale currents in particular, can play an important role in climate variability, and large-scale ocean circulation. So that realization making a very nice link for me between two topics of my studies, and this is an example of this link. Here we are looking at large-scale zonal patterns that are induced or created by the action of mesoscale eddies, those zonal jets that I was so excited about at that time. So yes, and today we'll talk more about this connection between mesoscale eddies and large-scale circulation. But before I do, I want to give advice to graduate students. If you need another advice from an old guy like me, Don't be too narrow in your studies. Never say that I don't need this course because it doesn't fit the topic of my dissertation. Try to learn more, try to stay broad, because when you have a broader look at the field, it will really help you in your path and your research later on. So learn as much as you can. Take courses that are different from the topic of your dissertation. You will thank yourself later. Okay, so having said that, let's move to the topic of today's presentation. I will talk about the importance of eddy-induced transport and mechanisms of this eddy-induced transport in the ocean circulation. Let me start from a few definitions. Right, all ocean phenomena, ocean currents in particular, can be broken into three main classes, depending on their spatial scale. You can talk about large-scale circulation, you can talk about the small-scale phenomena, and you can talk about the mesoscale, which occupies the space between the small-scale and large-scale. So mesoscale phenomena, mesoscale currents, that will be, for shortness, referred to as eddies. I know it's a terrible term, but it's a short word. Okay. Ocean phenomena on the spatial scales of tens to hundreds of kilometers. So they are loosely defined, not easily defined in data and numerical simulations. But at the same time, these eddies play an important role in the ocean and climate by redistributing properties sometimes called tracers. Basically, I'm talking about heat, salt, buoyancy, okay, and so-called passive tracers, biogeochemical properties, for example, like oxygen, dissolved oxygen, carbon, nutrients, different pollutants in the ocean as well. So these redistributions affect large-scale patterns in the ocean and can be important for climate, variations in climate, and climate change. So today we will discuss properties and significance of the transport by eddies. We will call it eddy-induced tracer transport, mouthful, right? And of course, it's a fascinating topic by itself, but it also has a strong practical motivation. Right? Most models that we use for the studies of climate do not have enough resolution in the ocean to properly resolve mesoscale. In fact, some of the models are beginning to resolve it, so they partially resolve mesoscale, which is a very dangerous territory. So you do have mesoscale phenomena, but they're heavily distorted by not enough resolution. So you need to find a way to represent the most important effects of these mesoscale eddies in this ocean component of climate models. And that's a strong practical motivation for these studies, because if you understand these effects, you can hope to model them or parameterize them in those numerical models that do not resolve mesoscale. So that's a practical motivation. At least this is something that we always put in summary of our proposals. All right, so let me talk about eddy diffusivity. It's one of the concepts that we'll partly challenge today. So it's a traditional diffusion, turbulent diffusion in particular, is a traditional way to represent mixing or stirring by mesoscale eddies. So the big assumption is, let's say, if C is a tracer, again, it can be salinity, temperature, biogeochemical tracer, and U is velocity, we can define large-scale components in this field. That definition is not unique and it's not easy, but let's say we can do it, okay, for the purpose of this talk. Then the main object for our study is tracer flux. that is due to the action of this mesoscale eddies. Mathematically, it's defined on the screen. You take the total large-scale flux and you subtract the component that is due to large-scale currents and large-scale variations in the tracer. The difference will be contribution from eddies. Everything else is from eddies, essentially. So a traditional assumption is that this flux basically mixing properties down gradient, so mesoscale eddies just homogenize properties. And if you make that assumption, there is a strong analogy between molecular diffusion and this turbulent process. And you can write this flux gradient equation on the screen, right? Basically saying that the flux is down gradient and the efficiency of this process is quantified by the property called turbulent diffusion. Strictly speaking, it's a tensor. It's although sometimes it's taken a constant, to be a constant. And this property, again, is important for modeling of this process. And in most models, numerical models that do not resolve mesoscale, you need to parameterize this whole concept, the diffusion, which means that you need to find this coefficient. It's called transport coefficient tensor, to be precise. You need to express this tensor, this function, in terms of known large-scale properties. So you run a model that does not resolve mesoscale, right? But it simulates large-scale fields. So if you can express this coefficient in terms of these large-scale fields, you close the problem and you know everything in this model. You don't need to resolve eddies, right? You have this wonderful parameterization, and you can just continue and publish papers. Okay, so as it turns out, this task is actually very difficult, if not impossible, to be honest. So we will talk today about the properties of this tensor and how you can move beyond this concept to improve the simulation. All right, so more on this tensor. So today we'll focus on so-called lateral mixing. So lateral means, in this talk, means horizontal in the mix layer, top of the ocean, and isopycnal below the mix layer. You can make some assumption that most of the exciting action by eddies is happening along isopycnals in the deeper ocean and horizontally in the mix layer. So if you make this assumption, your problem becomes two-dimensional. So strictly speaking, your tensor is a matrix 2 by 2. Right? With 4 different components. As it turns out, all 4 components are important for the mixing. That's the first piece of bad news today. Right. These different components of this tensor have distinct physical meaning. So you can separate this matrix into 2 components, 2 parts. The first one will be responsible for diffusion. So this is a part that's a symmetric component, and you can find the direction. You can rotate this tensor so it becomes diagonal. So and then the 2 eigenvalues that you see for this matrix have clear physical meanings. They are diffusion in 2 directions. Direction of maximal diffusivity, maximal mixing, and in the direction normal, perpendicular to that direction. So basically you can represent this diffusion, this is called anisotropic diffusion, by this diffusivity ellipse, right, that is oriented along the direction of maximum diffusivity. So, and as you will see later, these 2 values are indeed very different. So basically it means that most of mixing is taking place in this direction, and this direction is kind of secondary. It can be very different, as you will see today. So the second part is so-called advective part. That represents one of the advective effects of eddies. But we'll mostly focus on the first one today. By the way, if you have any questions, please let me know.
And that's just the symmetric and asymmetric parts. Of the
Yes,
right?
this is the symmetric and anti-symmetric
Yes,
part.
yes.
Yeah, exactly. Thank you. But you know, they have physical meaning. First is diffusion, second is pure advection, non-divergent. Okay, so it looks great on paper, but when people try to actually estimate these components and estimate this diffusivity from numerical simulations, they find incredible complexity in this tensor. This is one of these attempts by Ryan Abernathy and John Marshall, 2012, GGR, right? It's one of the definitions of the diffusion, and they show the map for the global ocean. So they used velocities estimated from altimetry, and use these velocities to mix tracers. So what they find is that the diffusivity they can derive from the studies varies a lot. Look at the range of numbers, right? And you're looking at the log of this. So the values change by several orders of magnitude. So there are huge variations in the diffusion, and this complexity is really worrisome, because if you want to parameterize these fields, well, basically, good luck. They were not the only one who found this strong, inhomogeneous distribution of the eddies. Another feature that makes this diffusion tensor complex is anisotropy. Anisotropy is the difference between these two eigenvalues, mathematically speaking. More practical terms, it means that the mixing in one direction is much stronger than the mixing in a perpendicular direction. So one way to estimate the diffusivity is to use Lagrangian methods, and this is what we did in a study with Irina Rypina and Pavel Berlov in 2012. Again, we used velocities derived from altimetry, and using Lagrangian method estimated the diffusivity tensor. So the results are shown by these diffusivity ellipses, right? And as you see in most of the domain, you're not, the ellipses are elongated. You're not looking at circles. Circles would indicate purely isotropic mixing. So you see that there are several places where this mixing is strongly anisotropic. So that means that that in addition to the value, you need to be aware of the direction, where the mixing is stronger than in the opposite one, in the perpendicular one. Right, so just an illustration of the anisotropy. So all this complexity motivated us to propose a study on the diffusivity tensor, right? And that was a study that was funded by NSF. And when we wrote the proposal, I wrote this proposal in collaboration with Pavel. It was one of those programs, collaboration between New York and at UK, at NSF, at US. And when I wrote the proposal, I guess I was incredibly naive. I was very young, 50. Anyway, so yeah. So we wrote in the proposal that we will just diagnose this tensor, study its properties, and propose ways to parameterize it. That somehow NSF believed us. But anyway, on a serious note, the idea of this project was to diagnose this tensor by so-called brute force from numerical simulations and study the properties, and hopefully that was supposed to help us to develop ways, to propose ways to parameterize this tensor. Parameterization again means that you can derive tensor diffusivity from large-scale properties and close the problem, so-called closure. So what we found was a big surprise for us. Okay. This is just one example, and it was one of the first papers on that topic that we published. Part of this study was to take a HICOM model it was a global model, but we took a part that addressed the circulation of the North Atlantic, and we used velocities from this model to advect different types of tracers, right? And so it's so-called offline approach. So we did it in the North Atlantic, and we were able to simulate different idealized tracers. And once you have a set of tracers, you can use any pair of tracers to exactly solve this equation. This is a flux gradient relation. So you can just, if you know the tracers in your model, if you know the fluxes in the model, you can calculate them. One advantage of numerical modeling is that you know everything in your model. Right? Disadvantage is it may be different from the real ocean, but yeah. Anyway, so you know the flux, you know the large scale gradient of the tracer, you can calculate the tensor. So this is an example of tracer anomalies in this model. Yeah, I guess the main point is you see these mesoscale features everywhere, which is the main topic of this study. So what we found, again, was a big and initially somewhat unpleasant surprise to us. We found that the tensor that you can calculate is so complex that there's no hope to actually parameterize this phenomenon, and you need to look for different approaches. So next few slides I will give you an example of these complexities. The first one has to do with anisotropy.
Igor,
yes, please.
So in the previous slide, or let me say, so did you start with there's a constant tracer everywhere?
With the constant concentration.
In other words, like, did you initially start with the tracer value constant everywhere around the model and see it accumulate, or was it initially, we use different tracers, and they all differ by initial conditions. So there is some kind of okay, so they're actually supposed to be like real tracers, like salt or.
We used a couple of tracers like that, but most of them are idealized. So you take a tracer with a constant zonal gradient or meridional gradient.
So you're not starting from a constant value everywhere?
No, that would stay constant.
Oh yeah, okay, so how is it, so you had areas where it was significant in area where there's not?
Right.
Okay.
For example, if I remember it correctly, one of the tracers would have a constant gradient in a zonal direction. So it would be high in the west and low in the east.
Okay.
And eventually it would, after a while, it would look like this because the areas would modify it. Thank you. Right, so you take a pair of tracers, you can inverse that relationship, you calculate your diffusivity tensor, and this is what you found. Fine. We expected anisotropy, the difference between two eigenvalues. What we did not expect is that these eigenvalues would differ by sign. Right? The first eigenvalue that stands for diffusivity in the direction of strongest mixing was positive. That is something that you expect. Positive diffusivity means that the areas would try to homogenize tracer in this direction, basically mix tracer in this direction. So that was not a surprise. The second eigenvalue would be negative. Negative diffusivity is hard to interpret. If you think about it, this this indicates that the eddies take a tracer anomaly, and instead of just spreading it and mixing it around, they would stretch this anomaly, forming a filament or a front. And then if they do that, then in the direction of maximum mixing, they will spread the tracer, right? In the direction perpendicular to that, they will squeeze the tracer contours. So this is why they stretch anomalies. So that makes sense, but you end up with positive and negative diffusivities, and negative diffusivity is, first of all, it's kind of hard to interpret physically, and then if you try to implement it in numerical models, it becomes numerically unstable, and your solution blows up. Numerical schemes do not like negative diffusivity. So that was the first surprise. We call this property polarity. So basically pairs of positive and negative diffusivities at each point. The strongest example of anisotropy. And again, you see the spread of values. Strong anisotropy, inhomogeneity in the values. What else? Yeah, but that was not the worst news. As we quickly realized that the definition of that diffusivity itself is non-unique. So the basic assumption of this whole approach is that turbulent diffusion depends on the flow, right? And so it should be uniquely defined. That is actually not easy to accomplish. There are two reasons for this so-called non-uniqueness. First of all, if you work with eddy flux, okay, well I hope it's not boring, but okay, if you work with eddy flux, any flux can have a divergent and non-divergent component. So the divergent component is the part of the flux that affects your property. As you know from your courses, if you have a heat flux, right, and the flux is divergent, that implies what? That implies cooling at that point, right? If it's convergent, that implies warming at that point. So divergence and convergence matter. If the flux is constant, it just moves heat around, it doesn't do anything. It doesn't affect temperature. Okay? It's rare for temperature, but it's possible for other tracers. So for this kind of study, you don't need this rotational non-divergent component because it doesn't do anything to your field. But what it does, it impacts the calculation of your diffusivity, and the difference is quite large. So this is a different study by Luolin Sun and Pavel, Michael, and so they estimate the diffusivity from the full flux on the left, and only the part of the flux that matters, the diversion part. The difference is 2 orders of magnitude. So if you're not careful about removing this flux, this non-divergent rotational component, you end up with a diffusivity that is 50 or 100 times bigger. Okay, so it sounds like easy to solve the problem. You just need to remove the rotational component. The definition of that rotational component, okay, now I become boring, is non-unique, right? There is no single way to do it. So it's a problem that is well known, but that gives you one reason, one cause of uncertainty in this kind of calculations. Okay, at least that was known. So this was something completely new to us. When you talk to people, when later we realized that they were aware of it, it turns out that the value of this turbulent diffusion depends on the tracers that you use to calculate. And this is crazy, because again, turbulent diffusion should be a function of the flow only. It should not depend on the kind of tracers you use. This is not the case. And if you compare these values for different tracer pairs, you see that the values will be different. And the difference is quite significant. Yes, of course.
To the pairs of tracers, right? Mm-hmm. So they're essentially idealized tracers.
Idealized tracers.
Well, when you say they're different, are they just initially distributed differently? Or
they initially distributed differently,
okay,
yes.
But otherwise they behave the same. In other words, like they don't have different inherent properties. So they're just pairs.
No, they're passive tracers. Yes, I see your question.
Yeah.
They're passive tracers, okay. So they're simply mixed by currents and nothing else. No
so you
sources.
did the experiment 2 different times with 2 different initial distributions of the tracers.
Exactly. And you can come up with hundreds of different choices. And you need a pair of tracers to calculate this tensor. And when you do it, you see that the tensor will be very different for each pair. And again, this is counterintuitive. It contradicts the basic assumption of the whole flux gradient relation. Yes, please.
It looks as if Arthur wants to ask a question in Zoom.
Yes, please. What do I do?
Yes, unmute.
He just has to unmute himself.
Arthur, you will need to unmute yourself.
You mean myself?
Yes, yes, I can hear you.
Yeah, I have a comment. So here, the different traces are the fact that you start from different initial conditions, right?
Yes, correct, yes.
Okay, so we're putting particles at different initial conditions in a nonlinear flow, which is chaotic, so it's no big surprise that you get different results.
Well, assumption, it was a surprise to us, first of all, and the assumption is that when you derive the diffusivity, that should be a function of the flow only, because that diffusivity is will be used to parameterize mixing by eddies. So if that assumption is violated, if you end up with a diffusivity that depends on the tracer, that means there is something wrong with the basic model.
Well, it's going to depend on the tracer concentration, and that concentration is going to depend on where these particles end up. And the particles from your initial conditions, it's chaotic, it's nonlinear, so they're going to end up in different places, which gives you different values of the gradient. So I don't think should be a big surprise.
Okay, but in that case, again, if this dependence is strong, it violates the flux gradient relation.
Can I ask a question?
Yes, please.
I will come to you with the microphone so Arthur can hear you.
It's a good point. I agree. But again, you have to be way too naive.
So, I don't know whether it's a question or a comment, but isn't both what you and Arthur are talking about is the fact that the diffusivity is dependent on, is geographically dependent, and therefore each particle, depending where it starts, is going to have this unique path through this field of varying diffusivity. I mean, comes to that, it's going to have time dependence too, right? Is that really what you mean?
I see your point, but in this simulation, the path of particles are always the same because they move within the same flow. By initial, I should clarify that by initial conditions, I mean distribution of the tracer. The flow is the same. I always start from the same point in time.
The flow that the tracer sees is going to be different because you're starting the tracer somewhere different in the field.
Yeah, I see your point. If you're thinking about in terms of Lagrangian terms, so you're looking at the particle that has a certain marker, let's say concentration of oxygen or some other tracer. So in all the simulations, we are looking at the same particle that moves around the same path in the domain. It's just these markers are different every time. So you end up with flow that can be described by diffusion that will depend on this marker. But the path is the same for all of them.
So are you, sorry to ask again.
Of course, please, go ahead.
So are you saying that you got this particle is in the exact same place, in the exact same flow field, and
Right.
all you change is the concentration?
Exactly. This is exactly what I.
Is.
Exactly. Thank you.
Okay, sorry, I was thinking somehow
Right, no.
it was spatial variability or something.
Excellent question. Thank you. Thank you. So it's the same flow, the same Lagrangian path. It's just we are looking at different markers or tracers, and our result will depend on that marker, and that is not supposed to happen. Okay. Right. This is just illustration of that dependence. So the actual diffusivity changes by up to 200%. It's a strong dependence. So we learned about these properties, and it looked pretty depressing. So it sounded like the turbulent diffusion model may not be a suitable framework for parameterization or for representing effects of eddies, or at least we should think about ways to expand it, moving beyond diffusion. So I still believe that we need to do it. I'm not saying that in the next few slides I will show you one idea for doing this. I'm not saying that this is the best idea or it will solve all the problems, but we should definitely think about other ways, more innovative ways of representing mixing my eddies, moving beyond diffusion. So, all right, so we decided to change a few things. None of these ideas are entirely new, I have to say, right? So first of all, we decided that to work with so-called eddy forcing instead of eddy fluxes. So eddy forcing is supposed to represent collective effects of eddies on a tracer. So it's not just a flux. So things become more complicated, but again, in numerical simulation, you know all these terms. So in addition to this term, which is a divergence of the eddy flux, the same flux that we worked with previously, right? There are some additional terms. This term is usually not important, but there are some additional terms that become important in some situations. So the advantage of this approach that you can include all effects of eddies. If you can think of additional process that should be included, the eddy forcing can easily incorporate it. It doesn't have to be in the flux form, right? So it's more generic and more direct. Another advantage is more technical. Remember I talked about the divergent and non-divergent fluxes, eddy fluxes, and that you don't need non-divergent component. With the eddy forcing includes a term that is a divergence of this flux. So that problem is taken care of automatically. You take divergence, so you eliminate non-divergent component. So you end up with terms that matter. So the assumption is that if you can get this forcing right in a model, numerical model, you will be able to recover the full solution. You will be able to recover the entire range of the eddy effects, including everything, and not just flux. That is more difficult. Okay? Any questions at this point? All right. Then the second, this idea is pretty simple. Okay. So we decided to expand the idea of diffusion, moving beyond diffusion, and in addition to the usual diffusion that is used to. Okay, so the next step, we define the eddy forcing. Now we have to model it or parameterize it by some kind of by the relatively simple means. So the idea is that you represent the eddy forcing in terms of large-scale properties. So the biggest and most difficult task is how do you do it? Right? If you are successful, again, you have a closure and you're done with the study, right? But the difficulty comes from finding the proper form. So traditionally, the effect of eddies is represented by divergence of the diffusive flux. Okay, the flux is shown here, right? So we propose to add an additional term, which is pure advection. Right? So now we have a combination of diffusion and advection. And again, they are trying to model the eddy forcing with using the large-scale properties. That's called parameterization. Okay. So you have these two terms, and you can rearrange it, and you end up with a term that looks like diffusion. It's a pure diffusive term. And you have a collection of terms, okay, that have a purely advective form. So technically speaking, advection comes from this new term that we propose to add, and the gradient in diffusivity. So now you have the combination of diffusion, mixing, and eddy-induced advection in the explicit form. And that approach, right? And then if you want to parameterize this problem, you need to find a way to express these two new parameters, diffusivity and eddy-induced advection, right, in terms of large-scale properties. If you can do it, then you have a closure. So the advantages of this approach is purely local, so you can diagnose these terms at any location, right? And the biggest advantage is that now advective effects of eddies, and later on you will see an example of such advective effect, can be modeled directly. So if you believe that the effect of eddies is advective, that can be easily, well, relatively easily addressed or modeled in this new approach. One example of this process is frontogenesis. And that frontogenesis is, the importance is indicated by positive and negative diffusivity. Yes, please.
Igor, why effective would it be right to interpret that as stirring? I guess we're
Large scale. Yes, large scale. I mean large scale advection. So that is a result of stirring. Eddy-driven frontogenesis is the example that I will talk about. So when eddies push together contours, forming sharpening up front,
right.
that would be an example. So kind of large scale stirring. Exactly.
Large scale stirring, but by the mesoscale.
No, not yeah, by mesoscale.
Okay, so you don't mean large scale stirring. You mean mesoscale stirring.
Right, mesoscale stirring that results in large scale advection.
Yeah.
I guess that's probably the best way.
Okay, so it's not divergent still. So it's not. So you're not interested in the rotational part. Is that what you're saying? It's stirring that leads to some kind of large scale advection.
It can be divergent, can be non-divergent. It can be confluent, so that would form a front. So the indication of that process is negative eigenvalues that we saw a few slides before. So if you have a negative eigenvalue, that indicates that the eddies stretch tracer contours, sharpening the front. And this is, we can call it frontogenesis. I am running a little bit behind. All right, 10 minutes? Okay, so just a quick look at the numerical simulation that we did, that Yu Yang Lu did. I just, all right. So he used the idealized model. It's a double gyre circulation. It's an isopycnal model, primitive equation model. It has 3 isopycnal layers. So this is the circulation of this model. So we call this feature a Gulf Stream. It's a strong current that is eddying, forming rings, warm and cold, right? And it corresponds to a sharp front in temperature. This is passive temperature, but it's similar to the real one. So you see, if you look at this field, so you see a sharp temperature front associated with this current, with this Gulf Stream. Okay, let me call it Gulf Stream, although it's probably looks very different. Okay, so in this study we can look at what eddies do to the distribution of tracer. So one property that Yu Yang studied was the formation of the front, so-called frontogenesis. So you can you can write the balance of frontogenesis equation, and then you can look at the processes that are responsible for sharpening of the front. Right? There will be some processes that will sharpen the front, and other processes that try to broaden it. And when you have a balance between the two, you end up with a stationary front. Okay? So what he found is that the two main processes that balance each other is a large-scale advection of temperature, in this case, and large-scale advection of temperature by eddies. So these two effects are shown as a time series on this plot. So positive means that the process sharpens the front, and the red line stands for the effect of eddies. The negative means that the process is trying to broaden the front, and the blue line here, which is negative values, correspond to the effect of large-scale advection. So you end up with this basic balance between large-scale advection that trying to broaden the front, basically create a large-scale front, a broader front, and the eddies that try to push these contours together, forming a sharp front, basically leading the frontogenesis.
Sorry to ask about
Of course, please go
It's
ahead.
so interesting.
Thank you.
So when you say front, do
thank you for asking. This is a temperature front.
So the question I asked was, does Igor mean the density front or the velocity front?
In this case, it's temperature front, but it can be any tracer front. It's a so-called passive temperature. So you put a tracer that looks like temperature in this model, and you study the evolution of the front temperature. Does this answer your question?
The large-scale advection is by the resolved flow, or is it the?
In this model, you resolve mesoscale eddies in this model, but you can separate it into large scale and small scale. So large scale is, in this case, is something that would be resolved in the climate model at some resolution.
So the large scale is trying to diffuse the front.
Yes, basically, I believe it's trying to create a front that is broader, more consistent with a large scale, and eddies do the opposite. Okay. Okay, right. Yeah, that's actually last slide. So we thought about, yeah, and it looks like it's a great opportunity to try this new approach, because we encounter a purely, let's say, advective effect of eddies. The frontogenesis can be easily represented by advection if the eddy-induced velocities simply, have a confluence and push the contours together. So we proposed a simple closure for this process. It worked well, although, yeah, anyway, but it definitely needs more work. So we basically assumed that this eddy-induced advection, that term that we introduced for this parameterization, is proportional to the large scale flow and has an opposite effect. So that at least that kind of relationship, the negative correlation between the large scale and eddy-induced, can be easily enforced in this new framework. You just make sure it's negative and proportional. That the same kind of relationship would be very difficult, if not impossible, to implement in a traditional diffusive model. How do you take diffusion and make it equivalent to advection? That is not an easy task. So, right, so that was 3 different simulations: no eddy forcing, full eddy forcing, and new closure. Well, hard to tell the difference here. So this is one of the measure of the magnitude of this gradient, of the sharpness of the front. So the dashed line is no eddy forcing, right? So no eddies, large scale. You see that the front is significantly more, broader, more diffuse, right? The full eddy forcing, the front in the full simulation is black line, and the result from the new closure is the red line, which is much closer. So you end up with a front that is much sharper and closer to the full simulation. So at least partly you capture the most important effect of eddies. And the closure itself is relatively simple. They are not saying that you should implement this closure, or this is a perfect solution, just a demonstration of the utility of the new approach. When you deal with eddy advection, it's much easier to represent effects of some of the effects of the eddies. Okay, that brings me to conclusions for the science part of the talk. So eddy diffusivity is incredibly complex, right? It depends on direction, space, time, and tracer. And the last part is most controversial and surprising, right? And also it's strongly anisotropic, and if you look at the diffusivity tensor, you find positive and negative pairs, which means that instead of just spreading tracer anomalies, eddies often create filaments of fronts. So they stretch eddy anomalies, and that implies negative diffusivity in one of the directions. Negative diffusivity is highly problematic, and it's unstable from a numerical point of view. It's just, I would say, non-physical. So it indicates that we need to extend or upgrade the traditional diffusion-based framework, and maybe look for ways to model the advective effect of eddies, right? Working with advective schemes. And the goal, of course, is the parameterization of eddies and models that cannot capture mesoscale completely, right? And represent such effects as frontogenesis. Okay, this is all I want to talk about today. So thank you for your attention. Oh, Yu Yang, good to see you. It's Yu Yang, who did most of the work for that I presented today. Okay, any questions?
So he doesn't have a question, or?
Oh, Yu Yang, you have a question?
Yeah, I do have a question.
You found
I think there's another question
mistake
in the chat first.
You found a mistake on one of my slides. I'm not proud, right? Go ahead.
I think, yeah, there's a previous question from the chat. Do you want to resolve it?
Question in the
From
chat.
the Zoom chat.
Chat.
Yes, from Marlos Goals.
Shall I read it?
No, can he talk to us, or she?
Okay, so I should stop sharing or how do I do it?
No, you use it.
Hello?
Yes, hello?
Yeah.
Hi, my internet.
Oh, hello, Mark.
Try to be brief, to complete on the chat. So, I know that some models, like the impact model, they have this backscatter of energy. It's back energy back to the system and include that energy in the model in front. And this too much diffusivity in the model, and they try to compensate for that.
Right.
Is this term similar to that the one you were describing, would be used in that sense?
Excellent point. The backscatter is a process when eddies, instead of diffusing properties and moving the energy downscale, they actually put energy back to the large scale field. And that is a process that is consistent with frontogenesis by eddies. So the eddies in this case would help to sharpen the front and speed up a current like Gulf Stream. So that is an example of so-called backscatter. And that in some sense corresponds to negative diffusivity. So yes, it is similar. But again, the implementation of negative diffusivity for tracers is difficult, if not impossible. So therefore, we argue for an advective form. Yes, but backscatter is definitely important for energy and momentum. It's an upgradient process. Thank you.
Thank you.
Thank you.
Igor,
Yeah.
I got a question.
Of course.
Yeah, thank you for the great talk first.
Thank you.
I just wonder, do you think how close are we to fully resolve mesoscale eddies in climate models? And is there a clear ocean resolution cutoff where that starts to happen?
This is a good question. It's an important question for you, Yang, because I think I will retire by the time it actually happens. But I guess at the resolution of, let's say, roughly speaking, 2 to 5 kilometers at mid-latitudes, you're beginning to fully resolve mesoscale. And if your computers are powerful enough so you can run a coupled model with this kind of resolution in the ocean, and there are some attempts like this, including the ones in co-ops, right? Then you don't have to worry about parameterization. But then you are beginning to ask questions, what happens at even smaller scale, and sub-mesoscale eddies, and mesoscale eddies at very short spatial scales, and always a phenomenon that you cannot fully resolve. So if you develop framework for capturing these small scale effects, you can use it for phenomenon at an even smaller scale, smaller than mesoscale. But it will be a while before we can run this kind of models in a coupled regime. But it's a great question. So
Thank you.
thank you.
I think Brian was before you.
Okay.
Okay.
Hi, Igor. Thanks. Fun and puzzling and fascinating work as always.
Thank you.
Yeah, I continue to feel that this discourse is being misdirected by words. In particular, the word eddies.
Oh,
A
yeah.
plural noun called eddies is a word that belongs to rivers and bathtubs, and it is little circulating things like that, right? And we borrowed that word from descriptive, folk fluid dynamics, and we borrowed it to mean, and we've made it into an adjective, eddy.
Correct.
Okay, but what we really mean by eddy is spatial high pass, right? If you replace the word eddy with spatial high pass,
Yes.
it's just more clinical, but it's clearer.
Right.
And when you use the word eddy-induced, I think that could be replaced with partition implied, and that would be clearer. These are partition implied things, not eddy-induced. There's no induction. And also, it is not eddies, which are little circular things. It is every component of the flow that isn't in the spatial high pass, that the spatial low pass takes out. And that includes some very coherent things that just aren't what we call eddies. So I wondered if you could partition the actual flow. The actual high pass flow could be partitioned into the part you could call eddies, little things that go round and round, just the rotational part of that, for instance, and then see what that does. And that might act more like a diffusion. Whereas, the entire spatial high pass component of the transport field is not eddies. It's not an eddy and it's not eddies. I think that language is just kind of getting in the way almost of progress here.
It's excellent point. You make several excellent points. Well, first of all, that separation into large scale and eddies is not unique. It basically depends on the high pass filter that you use. So you end up with two phenomena that are not necessarily distinct. But this definition, this high pass filtering definition, comes from the numerical modeling, because there you do have this separation. Then in that world, your large scale is something that you can resolve in your model, that you see in your model, and mesoscale or eddies, everything that you do not. So in the numerical model, that separation is clear, unfortunately. Right. When you look at actual phenomena, the separation is not clear at all. Sometimes you can really identify mesoscale features, but even in that case, it's not always easier to filter them out by doing the filter. It's a big and important problem. And so what we end up with high pass features, again, that can be in the form of waves, jets, filaments, vortices that are real eddies. So there is a whole zoo of different features that you do not resolve, and you have to parameterize somehow. But then again, that separation mostly comes from the world of parameterization numerical modeling. I do not think that this coherent features, vortices, will be more diffusive. I would say they will be actually less diffusive, because the coherent features that they have a distinct structure and clear propagation will be much more difficult to capture by diffusion than this entire zoo of things that I was referring to. That I'm not sure I agree on that point, but yeah, thank you.
I just think the terminology is confusing many people over generations, almost tragically. Just the word eddy.
I know.
It's just it's just a historical mess.
It is. Yes, I agree. But yeah, thank you.
Hey, I have a bit of a different kind of question. I think I recall that there was a team of oceanographers, possibly led by Jen McKinnon, working on, I think they call themselves the climate parameterization teams. So I was just wondering, I haven't kept up with what they've done versus what you've done. Can you speak to that? What kind of strides are they making in terms of better capturing parameterization phase?
There are several directions. Unfortunately, I'm not sure I'm familiar with that particular team. I know that that's my fault, not theirs. there are several directions. One of them is that backscatter effort, trying to parameterize, trying to model the effect of eddies putting energy back to large scale, backscatter. I know there was a team that worked hard on this problem. How to, most of effects are on momentum. So basically you're forcing, so if you have a front forming in, let's say, in the Gulf Stream, so that approach would energize this front by modeling this backscatter. I know that was one of the working groups working in that direction. There is also an effort to try to model the eddy forcing and the effects of eddies by stochastic means. And that is, I think, a very promising direction. I know I work with a group at NCAR that try to do it. So this way you're not, you're acknowledging the stochastic nature of eddies, and the forcing is not just a diffusion, but stochastic forcing that can stir properties and cause backscatter and so on. So there are several efforts around the world. Yes, it's a very difficult problem, that's for sure. Arthur has a question.
Okay.
Amy, please.
So, I want to maybe ask, I don't know if it was Marcos online.
He was here just a moment ago.
Or Brian's question maybe a little bit differently. So in climate modeling world, we're kind of getting to be able to do about 1/10 of a degree ocean resolution. So what would be missed or left to parameterize, or how would the simulation be wrong relative to that scale separation, which you just said would be like we need to get down like 2 to 5 kilometers?
That is a great question. I'm not sure I have the exact answer, but at 1/10 degree resolution, you resolve part of the mesoscale, maybe big part, and do not resolve the rest. So you will have this so-called, I guess you can call it eddy-permitting resolution. It's a term that comes from climate modeling. So you see phenomena like fronts, because in large scale model there is no Gulf Stream front. But you're beginning to see these fronts, but they're not sharp enough. So then the question is about sharpening. So that is exactly the question of backscatter and the question that we were trying to.
So they're definitely sharp enough in those models now.
Come again? I'm sorry.
Definitely sharp enough in those models. Maybe even too sharp.
That could be too sharp, yeah. Yeah, maybe that means we're missing something else. But when we always miss something. So when you partially resolve a phenomenon, you can. Yeah, the part that you resolve may be the most important, but maybe you're missing something else. So there could still be biases. Right? But then there are phenomena that we are not resolving, like sub-mesoscale. There's always something to do.
I think Arthur.
Arthur, yes, please.
Thank you for a really good talk. I really enjoyed it. I agree with Brian. The nomenclature jargon is a mess. A lot of what we're calling diffusion here is what Eckert, 7, 8 decades ago would call stirring.
Correct.
And I agree with you 100%. A new approach is needed. And I think out of all the many problems we have in GFT, I think this is an approach that is going to have to be based on AI. And the reason I say that is we've been doing everything with velocities on a Eulerian grid. We're not looking at the history of how these velocities are evolving. And for example, when you look at inertial floats caught in inertial wave motion, we do have we have positive diffusivity, then we have negative diffusivity, positive and negative, and it oscillates between those two values. And so I believe that the diffusion and stirring in the fluids is really feature-based. It depends on what feature it is. And to capture that, you're going to really have to bring in the time history of velocities following the particles to really get a feel, a better way to parameterize diffusion, and more importantly is the stirring.
Good point. But again, it becomes very difficult, so maybe AI approach can help, right?
Yeah, I don't have the answers on how to do it in AI, but we have a lot of young, smart people around. I think that's something that, needs to be worked on.
Exactly. Because if you incorporate the history, the time history of the evolution, correlation in the flow, that the memory in the flow, that can become critical. I agree. Good point.
I mean, where like features interact with each other to form bifurcation points, for example.
Mm-hmm. Yes.
That's very important because there you can see a great amount of eddy spreading. And any particles, are going to go into much different regimes. And then their history is going to be different. Their diffusion is going to be different. So yeah, it's feature-based, and that's where we should be going and trying to move away from trying to do everything with gridded values.
Okay, yeah, good point. Yeah, thank you.
Thank you.
Okay, John will have the last word.
Yeah, thank you, Igor, for a mystifying lecture. With all of the data that we have now, we have these profiling devices which have been all over the ocean, measuring temperature and salinity and some other properties. Arthur's point about utilizing AI, I mean, it should be that whatever it is that you come up with for a generalized solution should satisfy all the data that exists.
Yes, that's
if
for
the
sure.
data is correct. Of course, data is not perfect, but to the extent it is perfect, it should be possible to somehow set up a framework where you minimize the errors in your model, which is running and fitting the data in real time. I mean, the data exists, it's spatially diverse, and if your technology and your computation is correct, you should be able to test it by minimizing the deviation with this huge cloud of global data.
Yeah, I mean, one way to do it is to study data simulating models that do exactly this.
And we have an increasingly data-rich world. In the old days, we just had a handful of observations, and now we have this proliferation in all different parts of the ocean.
True.
And because these free drifting profilers have been carried by the current to wherever they are, you should be able to somehow generalize this. And I can't tell you, like Arthur, I can't tell you how to do it, but it should be doable somehow.
Well, Argo data are used in models to validate models and data simulating models. So that's a great resource.
Yeah,
for sure.
Well, thank you for a provocative talk.
Oh, thank you.
Okay, thank you very much, Igor. Thank you all for coming. We will have 2 more faculty seminars next week by Cassie Gaston on Wednesday and Ved Shirayev on Friday. Both are candidates for promotion, so they will be really important seminars. And I hope everybody will come again, and maybe even a few more people. Tell your friends they should all come, okay? Thank you very much.
Thank you.
Very nice talk.